Let's jump right into this explainer. Today, we're exploring the fascinating IRDS roadmap for the future of large-scale superconductor electronics and quantum computing. You know, we're literally looking at a pivotal moment in technology right now. All of this is drawn directly from an incredibly comprehensive presentation by Dr. D. Scott Holmes on the International Roadmap for Devices and Systems, or the IRDS for short.
This quote absolutely hits the nail on the head. Back in 1900, if you asked an engineer how cars would be powered in the future, you'd get three completely different answers: gasoline, electric, or steam. The winner wasn't obvious at all. Well, today, we are facing that exact same kind of paradigm shift, but this time, it's a wide-open race to build the computers of tomorrow. So, just as inventors a century ago battled over the automobile, today's engineers are racing to overcome the heat, power, and speed limits of standard silicon. We're looking at a modern track featuring three massive contenders: advanced digital logic, quantum computing, and brain-inspired neuromorphic designs. To make sense of it all, we're going to break this complex race down into 6 distinct heats. We've got the next computing race, superconductor digital logic, the quantum computing contenders, building fault-tolerant quantum, accelerating digital computing, and finally, brain-like superconducting computers. Okay, let's get into it.
First, Section 1, the next computing race, focusing on preparing for large-scale applications. Before we talk about the contenders, we really have to understand the sheer scale of the racetrack here.
The crucial point is this. For superconductor electronics to truly revolutionize our world, we've got to achieve large-scale applications that require more than 1 million switching devices per chip. 1 million! That is the critical threshold identified in the IRDS roadmap. So we're not just talking about small lab experiments anymore. The future absolutely demands massive, scalable integration to meet our computing needs.
Moving on to Section 2, superconductor digital logic, or the fast-paced contenders. Let's look at the specific engine types, the digital logic families that are competing to run these massive systems at cryogenic temperatures.
I know, that's a lot of dense acronyms, but each one represents a completely different way to process signals efficiently. They're all trying to balance switch count, energy use, and clock frequencies, which, by the way, can reach a staggering 21 gigahertz. For instance, you've got RSFQ offering super rapid switching, while ERSFQ focuses more on energy efficiency, actually bringing zero static power dissipation to the table. They're all vying to be the ultimate building block of future supercomputers.
So, with all these logic families being evaluated on metrics like area, logic depth, and scalability, we have to ask ourselves, which one is going to emerge victorious for digital circuits? Is it going to be the high-speed AC-powered chips? Or maybe the incredibly energy-efficient adiabatic designs? The roadmap is aggressively searching for that winning combination.
That brings us to Section 3, the quantum computing contenders. It is a crowded field. Let's step into the mysterious and, let's be honest, incredibly hyped world of quantum computing. Much like our 1900s automobile analogy, there isn't just one single type of quantum computer being built right now.
As you can see, the trade-offs in this space are incredibly stark. Whether you're trapping ions or using superconducting nonlinear oscillator circuits, every single approach has massive technical hurdles alongside its incredible potential. Notice how trapped ions give you long lifetimes, right? But then they suffer from slow gates and literally require a vacuum. Meanwhile, superconducting qubits offer blistering fast gates, but they demand extreme, near-absolute zero system temperatures. It's a real balancing act.
Looking at the projected roadmap stretching out to 2030, the sheer scale of qubit growth requires us to do something pretty drastic. We have to move our control systems from room temperature down to 4 Kelvin. This means transitioning to superconductor electronics to manage the delay and power constraints. Think about it. You simply cannot run wires from a room temperature controller down to a massive quantum chip without introducing way too much heat and signal delay. The control essentially has to move into the freezer right alongside the computer.
All right, Section 4, building fault-tolerant quantum, or the path to reliability. Because, let's face it, raw qubit numbers don't really matter if the calculations are just full of errors. So let's explore how researchers actually plan to achieve fault-tolerant quantum computing. Because without error correction, all that immense processing power essentially just creates really expensive noise.
Enter the cat qubit. This is a very promising superconducting approach where the bit flip lifetime is a staggering 44 minutes. Yes, that means the system jumps states only about every hour.
Now, while their phase flip lifetime is still short, this autonomously protected design means they basically just have one dominant error type. And you know what? That changes everything for error correction. It's absolutely fascinating. By designing a qubit that is inherently resistant to one type of error, the bit flip, we can focus practically all our error correction efforts on the remaining problem.
So, the big takeaway here is that smarter qubit designs, like the CAT qubit, directly solve the massive physical-to-logical qubit overhead bottleneck. Instead of needing thousands of physical qubits just to cobble together one reliable logical qubit, targeted approaches like this could dramatically fast-track our timeline to practical, actually useful quantum computers. It's a real game-changer. Section 5. Accelerating digital computing. We're talking data centers in a shoebox. Shifting gears away from quantum for a second. Let's see how these supercooled components can totally revolutionize traditional digital accelerators and application-specific integrated circuits. This is all about making massive computation incredibly dense and incredibly fast.
Imagine taking massively heavy computation tasks, like, say, processing the support needs for a 240,000 qubit quantum computer, and handling all of that with blazing fast, energy-efficient chips. Superconducting circuits basically allow us to strip out the heat generation that currently limits how tightly we can pack processors together in standard silicon.
But what's truly mind-blowing here is the projected scale. We are talking about packing an entire data center's worth of processing power into a volume roughly the size of a shoebox. This IMAC vision utilizes roughly 500 billion Josephson junctions. That represents a complete paradigm shift in computational density. It completely bypasses the physical space and cooling limitations that plague today's massive data centers.
Which brings us to our final heat in this race. Section 6, Brain-like Superconducting Computers, or Optoelectronic Intelligence. Let's look at arguably the most futuristic contender on the roadmap, neuromorphic computing. This is where we literally stop trying to build better calculators and we start trying to build synthetic brains.
Well, it turns out that the natural spiking behavior of Josephson junctions is almost a perfect biological mimic. It allows pulses to travel on strip lines without the usual delay issues that hinder standard spike-based computing. Nature uses a spiky neural network, and so do these specific superconducting circuits. That makes them an incredibly natural fit for next-generation artificial intelligence applications. Let's look at how this actually scales. It builds from just 8 junctions per synapse into a massive optoelectronic intelligence network using photonic interconnects. It starts out remarkably simple, just a few junctions simulating dendrites and synapses. But by leveraging those photonic links, researchers are aiming to scale this all the way up to full 300mm wafers, hitting around 1 million neurons each.
And if you combine 1,000 of those wafers, that massive stack would result in a 1 cubic meter system containing 1 trillion synapses and over 100 trillion Josephson junctions. We are talking about a physical footprint roughly the size of a standard washing machine, but housing an optoelectronic system of just unimaginable complexity.
But get this isn't just about matching the human brain. This roadmap actually envisions a system operating 65 times faster than our own biological synaptic capabilities. It basically takes the structural genius of biological neural networks and supercharges it with the raw, frictionless speed of superconductor electronics. No way, right? As you can see from this complex web, advances in digital circuits, quantum error correction, and neuromorphic designs are all converging on the IRDS roadmap for the coming decade. None of these technologies exist in a vacuum, you know? Improvements in cryogenic memory or digital logic will actively push forward the realities of both quantum and neuromorphic systems. They all feed into each other.
So, as we look at all these incredible contenders, I have to ask you, who do you think will emerge as the gasoline engine of the 21st century computing race? Just like that pivotal moment back in the 1900s, the eventual winner isn't obvious yet, but the race to build the future of computing is undeniably underway. Thanks so much for exploring this incredible roadmap with me.